This is part of Simplified revision series. Okay. And in fact, this is part 2 of measurements. Part 1, we did topics pertaining to errors in measurements and then uncertainty quantification. That kind of aligns a lot with statistics. Okay. In this part 2, I'm going to do measurement devices. Okay. PYQs concerning measurement devices. And there is a very, very nice gate question at the end of this session. Notice there is a question from 2023 paper, which I didn't give a solution for. Okay. What I'm going to do was to find a solution at the end of this meeting. So there are about like 7 problems or something like that. We'll quickly finish it. It'll take about 30 minutes or something like that. Then it's almost sort of like a competition. Okay. I'll help you find the solution. The task is for anyone to find the solution. Whoever finds the solution, okay, kind of would be impressing me, and it's a very, very good sign your preparation. Okay. Good quality check for your preparation. And I would be really impressed if you can find the solution. I can certainly help you find the solution. Let's say if it takes, say, even 15 minutes, 30 minutes, I'd be willing to spend that and see whoever finds the solution for this one. It is not out there because I didn't put it up during 2023 solution, but we'll discuss the solution today. Okay, that is the objective today. And let's quickly get started with this measurements thing. See, notice in measurements, we have some topics intersecting with engineering mathematics, right? This uncertainty quantification that we did. Now, typically every year there is a question from AC bridges, okay? A question from one of PMMC, MI dynamometer. Then there are some miscellaneous combination questions. So we're going to look at the second part today, okay? And this is part 2 of this particular measurement PYQ discussion. Okay, let's quickly head back to questions. First one, there are some recall based questions. I'll do is I'll put a table of typical bridges, RLC measurement bridges, and what they are used for. Okay, name of the bridge and their use. I'll quickly put that up. But for now, quickly let's answer these two PYQs concerning that. Which one of the following bridges cannot be used for measuring inductance? Being can be used. It can be used for frequency. It can also be used for inductance. Okay. Hay can be used. Oven also can be used. Okay. What cannot be used is the sharing bridge. Typically remember it as C for capacitance. Okay. So this cannot be used. That makes it the correct answer for this question. You give a list of things that you need, and a list of bridges for other things. And among these, Maxwell bridge, Hay bridge, Series 7 bridge, then can be used for measuring inductance. So what is the difference? There is something called the Q value. Okay, they differ based on whether the Q value is high or medium. Okay. So let's quickly answer this one. We have Maxwell bridge, Kelvin double bridge, Hay bridge, sharing bridge. Okay. I just said notice. I remember she is sharing for capacitance. Okay. Yes, some. And then double bridge is a interesting bridge that is kind of used to measure low resistance, Okay. Potentiometers can be used to measure resistance. Low resistances. The circuit shouldn't affect that resistance measurement value. Need to slightly be clever about it. And that's what Kelvin did. Okay. So this is QK. Yes, some. Can we answer this at this stage? QK, some. No, we cannot answer. Okay. Give you one more mnemonic. So Hay can be used for Q coil. Kelvin can be used for Q coil. And H for high. Okay. H for high Q coil. So He goes to Rn, and I suppose QK, Rn, SM. There goes our answer. And P, the other Maxwell-Wien bridge, that can be used to measure medium Q coil inductance. Okay. Anyways, I'll give you the complete list of things here. There is typically, there is a recall based question, which bridge is used to measure which. And there is almost every year there is a question from AC bridge. Okay. AC bridge, what you need to know is this. We put up a lot of videos on impedances and all that, right? If you know impedances, you can handle AC bridges. Okay. So typically, let's say you take the output here. Okay. In fact, you don't take the output. You're trying to measure something in one of the bridges. Okay. And there is an input to the bridge 7. Okay. Now let's label these four Z1, 2, 3, E4. We are discussing as AC bridge lens condition. Okay. Now, just like DC bridges, DC Wheatstone bridges, AC bridges has the same similar equation. Okay. What you got as Z1, impedance Z1, Z2 equals Z3 by Z4. So this by this equals this by this. You could also write that as Z1 by Z3, right? By taking this term here and this term there equals Z2 by Z4. And the same, rated right way. So it's Z1 by Z2 equals Z3 by Z4. Okay. The same pattern that also shows up in the bridges, easy Wheatstone bridges. So no surprises there. Okay. Balance condition. But what you need to know is this is actually two equations because Z, the impedances are complex numbers. There is a real part, the imaginary part. Real part in the LHS needs to be equal to the real part in the RHS. Imaginary part in the LHS needs to be equal to imaginary part in the RHS. Could say this is two equations. You could also say, in other words, the amplitude has to be the same in the LHS and RHS. The phase has to be the same in the LHS and RHS. Both are one and the same. Okay. But notice there are two equations here. Okay. Quick example is this question for a balanced oven bridge circuit and the figure values of LX and RX are. Okay. Let's we have a capacitor here, resistor here, and then we have a variable capacitor resistor here and some unknown things over here. Okay, the X things are all unknowns, I suppose. So you're going to change this variable capacitor resistances until there is a balance in this bridge. In the change values and this known values of C1, C2. Okay, you know R2, you know C1, and then you are changing this, you know what the change values are. So you know C3, R3. The bridge is balanced at this stage, you can find out what is LX, RX. But what are the conditions for that? It goes down to what I just said. Notice we need to have four things here. So let's say this is Z1, Z2, Z3, Z4 or ZX. Okay. Let's quickly write down what the four values are. We have Z1, it's impedance of a capacitor. Can anyone say what this is? So if you are capable of answering this, this is 1 by J omega C1. And then you have Z3 is fairly easy. Or to avoid any confusion, let's just call this 2 and let's call this Z3 because the labels are 3, 2, 3 and 3 here, 2 here. Z2 is fairly easy. This is just R2. Okay. And then you have Z3 first, 2 in series. Okay. So you have R3 plus 1 by J omega C3. And then the fourth one, we have C equals X plus A omega X. Omega is typically the operating frequency. Let's write down our condition. That's our condition I just said as Z1 by Z2. Z2, Z3 doesn't matter, okay? Let's say Z3 equals 2 by X. Okay. So if I were to write that down over here, what I have here is 1 by, let's kind of, write it down in a convenient form. I have 1 by J omega C1 in the numerator. This is Z1. Z3 is X plus J omega. That needs to be equal to Z2, that is just R2. Okay. By Zx, that is Rx plus J omega. So notice there is a real part to the LHS, imaginary part of the LHS. You have to simplify this. Simplest way, okay? Now, don't make this the complex number, how do you simplify LHS? How do you simplify RHS and all that? And all that can be tricky if you do it the incorrect way. Easiest way to do that would be, notice if I multiply this with this or the real part. We also got the imaginary part. Very easily. Real part is R2 RX. Imaginary part is R2 J omega LX. I easily got it. Similarly, if we multiply this and this, RX into that will be imaginary. One because there is a J. J omega LX into that, there is a J omega here, J omega there, J omega will get cancelled. There will be a real part. Okay. So instead of simplifying LHS into real and imaginary, RHS into real and imaginary, we'll do one small, one smart thing here. Just quickly multiply these two things. Okay. So I am going to write it that way, and I need some space. So I'm going to need space. Fine, let's kind of write it down over here. Okay. Now this what I get as Rx by j omega c1. Lex by c1. The j omega got cancelled. Equals R2 Rx, okay, plus R2 j omega. Is this correct? I am sensing something fishy. Yeah, I wrote it. Repeated z3. Okay. Last one is supposed to be zx. This denominator is supposed to be zx, right? This is in fact, this was correct. Rx plus j omega lx. This is supposed to be z3. This is supposed to be c3, and that is r3 1 by j omega c. I mean, the same command that I made earlier holds good. So if we multiply this and this, if we multiply this and this, there is a real part, imaginary part. I can easily split that up. Okay, let's write that one. So I got Rx by j omega c1 plus Lx by c1 equals R2, R3. Let's write the real and imaginary parts in different colors. Okay, I'm going to write the real part in red, that it's more clearly visible. The real part here would be Lx by c1. The real part here would be R2 by R2, R3. Okay, there is an imaginary part here that would be R2 by j omega. Comparing the real and real, now Lx is R2, R3, C1. Lx is R2, R3, C1. Okay, and Rx is R2, C1, C3. Or Ax, okay, is R2, C1, C3. So in fact, it says R2, R3, E1, C3. There is a mistake there. The mistake difference there. Okay, and Rx happens to be, if you take there is R2 there, it will get multiplied by C1 from this term, j omega will cancel, and then you have C3 in the denominator. So this term is correct. Okay. The answer here is. Again, let me repeat. If you try to simplify LHS and RHS separately, you can quickly run into trouble. In fact, notice, while I was writing this, be careful about the indices, okay? This is E1, R1, R2, R3, R4. But you have to use a question index so that you don't run into any issues. This was, I was trying to use Z3 here, okay? Sorry, I use ZX. Using Z3, you can quickly confuse what is what, okay? So bottom line on Z2, there are two parts here. There is a real part, there is an imaginary part. Real plus imaginary, LHS, and then you have real plus imaginary in RHS. Real plus imaginary in RHS. The equation to be correct, both has to be correct. The real has to be equal to the real, imaginary has to be equal to the imaginary in both the sets. Okay, it's not a division again. The LHS can be split into this. This can be split into this. There is a question: how we got R1, R2, C3. I don't know how you got R1, R2, C3. Where did you get R1, R2, C3? This is Rx. Right? Where did you get R1, R2, C3? You are mentioning something incorrect, okay? But how I did it, that's why I color coded it. Oh, that is also not C1, is it? So I have a C1, and it's R2, R3, C1 is there. Then this happens to be Rx, happens to be R2, C1 by C3. Again, let me tell you, whoever is asking this question, you are unnecessarily using me also at this stage. Okay? You're asking me how I got the option. I can explain. Because you are telling something incorrect and telling me how did I get that. And I am wondering how did I get that, right? Because I didn't get that, number one. If you ask me how I got what I got, I can explain you that. I did not get R1, R2, C3. I did not get R2, R3, C3. Okay? What I got is equated the real parts here. There is no J term here. So LX is R2, R3 into C1. Two options, I suppose. Either this or this. Then this part, the yellow part, that's the imaginary part because there is a J there. Equate those two. Notice Rx will be R2 by C3 into C1. So R2 C3 into C1. Okay, fine. Let's go to the next one. Has to do with, PMMC. This is fairly easy. There is one formula and they keep asking questions based on that. There's a Tere Bina. Yeah, the mnemonic that I use is Tere Bina, right? There are a lot of Hindi songs, I suppose, right? T equals BINA. Let's also give this some colors. Equals. I can write it here. Okay. T, torque in the PMMC. Okay. Equals BINA. Tere Bina. Right? So what is B? The B, magnetic flux density, sectional area of the coil, that is this. Number of turns in the coil is this. The I is given over here. What they are asking for is the deflection. Okay. So most of you know that there are different types of bridges. We will go. Let me finish this question and answer that. Okay. So notice what you need to know was, so most of you know, right? A force equals K times X in a linear spring. Torque equals K times theta in a torsional spring. Okay. So in a torsional spring, this happens to be K times theta. F is Kx. Most of you know that relation, right? My is E epsilon. Right? If it's Kx in a spring. Torque equals K theta in a torsional spring. This normal spring that you know. And in a PMC, a torsional spring is used. What they are asking for us, in fact, this K is given. What they are asking for us, how much is this theta? Okay. So what is given as P is given, I is given, A is given, even K is given, they want to know theta, right? That's fairly easy. You can write theta as I and A by K. Okay. And you have to put that in SI units, you should be good. You want things in degrees, notice you want the answer units. Okay. Other than that, I'll put everything else in common SI. This is Newton meter, for example, torsion, right? This is in centimeters. I'll put all of that in SI. I'll leave just the answer units as such. So I won't test this degree because I want the answers in degree. Okay. Notice K is in a denominator. So this is 1 by degree that goes to a numerator and becomes a degree answer. Everything else should get cancelled. Okay. And so let's write it this way. In SI, this is 1.5 Tesla SI. Okay. Again, let's leave it as such. Let's not worry about it. And then, yeah, I will change this. Okay. 2.5 into this, I'll change into 2.5 into 10 power minus 4 meter square. Number of turns, I'll leave it as such. This is 100 into 10 power minus 6. This term is I, okay? And what I'd be inputting is 100 into 10 power minus 6. So let's quickly make that substitution, find out what the answer is. 0.5 into 100, 10 power minus 6 into 500 to 2.5 into 10 power minus 4 by 5 into 10 power minus 6. Find it out if you want to, quickly simplify any of this. Quickly find it out how much is this. Even some of the things on this that will get cancelled. In 5 into 1.5 by 2. 2.5 into 1.5. There is also a 5, right? Okay. Just confirm whether you're getting this. 9.375. The answer happens to be 9.375. And because we retained this degree, your answer should be in degree. Most other terms should get cancelled. Okay, now there is a question. What are the different types of bridges we should go through? See, we have gone through all the DC bridges. Even in circuits and all that, we discussed all the DC bridges, right? The AC bridges, what you need to know is this. Z1 by Z2 is Z3 by Z4. You need to know what impedances is. Given any bridge configuration, you can actually find out the balance condition. Knowing this complex algebra, complex variable, this algebra, right? Impedances that you need to know. So whatever is given here, you can quickly calculate. 2 more questions are like this. Typically, 1 more questions are like this, recall based. Which is that I'll give you a list of which is used, which is there and what they are used for. Kelvin is used for low resistance, Hay bridge, Shering bridge, Wayne bridge, Owen bridge, Maxwell bridge. What is being used for? I'll give you that list. You need to know at least that much so that you can get 2 or 3 marks here in measurements. Not 2 or 3 marks, 1 or 2 marks in measurements. Okay. In fact, if you ask me what is the thing that you need to know, I would put this AC bridge balance condition and recognizing it as 2 equations. Would say, real image apart, you could also say there is an amplitude and magnitude. If you can do that, that is at this stage more than enough, okay, for the gate PM paper. Moving coil voltmeter has an internal resistance of 50 ohms. Scale of the meter is divided into 100 equal divisions. When a potential of 1 volt is applied to the terminals, deflection of 100 divisions is obtained. At this stage, what it says is, this is full scale current. That system leads to full scale current. Scale has 100 divisions. Volt results in 100 divisions. So that 1 mole corresponds to I full scale. Scale is full. 100 is completed. Of course, the voltmeter, you should be able to measure higher voltages. That's why you add the shunt voltage. Okay. Or decide that when a potential of 500 volt is applied to the terminals, deflection of 100 divisions. Yes. Now we want to measure the same thing with a 500 want to measure 500 volts with the same thing. Okay. So this is the circuit. This is this internal resistance, RS. Okay. And this is where you're measuring this across. Okay. This is a circuit. Now you are changing this to this. Right. The circuit is this. Okay. So in fact, this bit, let's draw. This is going to what? This is what I'm going to measure. Okay. This is outside of the voltmeter circuit. What is in gray is the thing. Okay. So I'm measuring the rows. Whatever is in this side is the circuit. Notice you want to be able to measure a higher voltage. Typically, what we do is we add a shunt resistance. We change the circuit. We have switches, simple switches to do that. We add a shunt resistance so that if you're trying to measure 1 volt, let's say this RS happens to be 50, right? So the full scale current, if yes, okay, we're measuring the maximum scales. What is the current in the circuit at this stage? What is the current, full scale current at 1 volt with an internal resistance of 50? So what is the current I full scale there? What is the current in the first circuit? Okay, 20 milliamps, I suppose, right? 20 milliamps. So if this current is flowing through that ammeter, whatever is happening, it is showing the maximum. Yeah, that's fine. It's showing the maximum allowable. Only there is so much space in the scale. Okay, it cannot go beyond that. If the current goes beyond that, the scale is getting stopped. Right. This is 1/50, 1 volt by 50 amps. Now in this scenario, we are going to make a change to the circuit. That is, we are going to add a R shunt. Okay, the internal resistance remains the same, but in this scenario, new scenario, we want to be able to measure 500 volts. We modify the circuit by adding one more shunt in the thing. And when you put 500, you want again 100 divisions. That is, this should result again in full scale current. The current here should again be Fs. That is 1/. When you're measuring 500 volt, you can only do that if you have a shunt resistance. And at 500, you should get full scale. That current will give you the full scale deflection. So this is 1/50. And RS, that is already 50, right? So now the question only unknown here is, what is this RSH? That can be quickly found out. So the voltage, let's say if your voltage drop, the 500 volt current is this, how much is the voltage drop across RS? I into RS, that is, there is a 1 volt drop across the internal resistance. Till here, there is a drop of 1. Okay. So total rise is 500. There is a drop of 1 here. There needs to be a drop of 499 across the RSH. Okay. So if you ground this current, you have a drop of 1 volt across RS. You need the rest 499 volt drop across RSH. So Fs into RSH has to be equal to 499 volt. Already know IFS. Can you find what is RSH in this case? Implies RSH happens to be. Notice, this value. The full scale value. You're wondering what that is. You can again color code it. IFS. RSH is 499. IFS is this 1/50, 20 milliamps, I suppose, right? 20 milliamps. Don't know what this is. Yeah, the answer here, so solving this RSH is what they are asking for. 4950 ohms. Okay. As far as you recognize by voltmeter, they are referring to this circuit. And, to measure a higher voltage, you need to add a shunt resistance. This circuit becomes this circuit. Actually, answer this question. Notice this is just a V is IR, right? Easy. But understand what the voltmeter is and what they have given in the question. Description question, you should understand. If you understand that, it is actually very, very, very easy circuits question. The real trick is, hey, can you understand this? Right. And quickly, for the voltmeter, the shunt is added in series with the internal resistance. In ammeter, you will be adding it in parallel with the internal resistance. Okay. This is in series. If it were an ammeter, you will be adding it parallelly. So that again, you don't, you let most of the current, you give an alternative route for most of the current, higher value current. Okay. So the deflections are still controlled. Okay. Okay. With that pointer, notice I'm done with most of the questions. Okay, 10, 15. Yeah. Done with most of the questions. This is the last question. Okay. So what I said is, this is a question from 2023. We discussed solutions of 2023. I didn't put up solution for this one question. Okay. Right now, I'm not going to give the solution. I'm going to test who can figure out the solution. Okay. Every year I like to give, one hard question. You should be learn things outside of gate, right? So spoon feeding doesn't happen in the real world. And at least one class I allocate with not an open-ended problem, but with a problem for which the solution is not out there. Not, you cannot Google this, find the solution, something like that, right? It is not out there. And right now you are going to find it. I can, of course, help you. I can give you hint you, make you think along directions and all that. Okay. That is what I am going to do next. Before that, measurements, fairly easy. Quickly look at dimensions, units. First of all, units, most of the mark silly mistakes is made there. You want to be convenient about it. Dimensions, actually, you can verify, eliminate a lot of questions. In that sense, there is very useful tool to know. Okay. In medium mode, many of those things, there are typically accuracy, precision. These are fairly basic questions you should know. And almost every year there is a question on this. Sum of two Gaussian random variables will be a Gaussian random variables. Means add up, variances add up. Standard deviations do not add up. Variances add up. Okay. Know that. Again, this is something that is very useful to know. Area, if you take the Gaussian distribution, one sigma deviation, within that the area is 68%. 68.5 something. Okay. And then if you take two standard deviations, the area within that, the dotted area, yellow dotted area is going to be 95.5%. 3 sigma, I suppose it's 99.7%. That you need to know. And there were some special cases, right? How if you combine two data, what happens? Okay. There's also with that regression is a time consuming problem. I told you a couple of shortcuts. And then even if you want to find the regression coefficient, the easiest way is this. If you want to find it accurately, okay, the easiest way is this, because you just need to fill up two easy columns to do all the summations. That also I did. Okay. But typically this is a very time consuming question. Decide when you want to do it. Typically do it at the end of the exam if we have spare 10 minutes. Otherwise, skip this question. Okay. Guess something reasonable and skip it. You need to know as far as the bridge balance is this. AC bridges, you need to know this bridge balance condition and to ability to deal with impedances, complex variables or complex numbers. That you need to know. If you know that, and if you also can recall some basic bridges and their uses, you can answer these questions. Okay. So we are done with this. Torque PMMC is this, dynamometer and all that. I think we can put it aside. Voltmeter, this is a simple circuit that shows up. Again, questions are fairly easy. That brings us to question number 7. Okay, so before I start that, are there any other doubts pertaining to this measurements? Number 2, it may take 15 minutes, 30 minutes, 45 minutes based on how fast you take to take it. You want to do this exercise? Those who are here right now, do you want to do this exercise? Impress me by finding the answer. I can certainly help you, but do you want to find the answer? Because, let's skip this. There one question, regression question itself, you have decided to skip this one question. Who bothers? One question out of 4 years PYQ, 5 years PYQ, we don't care. We can afford to skip it. Is that the scenario, or someone wants to find it? While I wait for an answer, see, typically most of you are finishing at the beginning stages, finishing the exam by one and a half hours and all that. Okay. Learn to sit for 3 hours in the examination. On the examination, you'll be forced to sit. It's not like I'll finish in 45 minutes and I can get out. Okay. You'll have to stay there for 3 hours, right? So during practice, also start doing that. So consider this now in 45 minutes, 1.5 hours, you are done with the examination. Most of the question, this one question is, say, only is left. Many of you would attempt to solve it. Any of you interested, or we'll just move on? Okay, let us try. Let's find it. See, okay, so you have to find. Okay, some of you are interested. Okay, for the first 5 minutes, how do you connect this? There are some various numbers, various details. Can you at least list down ideas that would be somehow related to this? Some of the ideas that we know very well, of the ideas that we don't know, but can you try to at least list down ideas that would be very useful here? You don't need to know what an integrating voltmeter is. Okay, to answer this question, let me also say, sir, I don't know what an integrating voltmeter is. Fine, you don't need to know that, right? There is a minimum average time required to yield a 99% accurate result with 95% certainty. At least the related concepts you should know, right? For many concepts that we have discussed. Okay, one concept that is there in the practice question, problem sets, diagnostics, and all that, but it didn't show up in the PYQ still now, but it showed up. Okay, it's also there in the class notes, but it showed up for the first time. I'll tell you what that concept is. That's fairly easy. But rest of the concepts or ideas involved, you should be able to grasp. Let me start underlining some of the things. Okay, some easy ones. Actually, you know how to deal with this. 95% certainty. That is related to something that we know very well. At least we have discussed quite often. It is band limited to a spectrum of 5 kilohertz. That is actually related to, again, one more related concept. Okay, so I should give a lot of credit to Guru. Is this related to 2 sigma? Area under the Gaussian curve is 95.5%. Is it related to that? Yes. Okay, you got one connection made. One, at least you identified one concept. It's band limited to 5 kilohertz. Yes, a Gaussian noise, plan spectrum, and all that. It's band limited. But that word, forget 5 kilohertz. It's band limited. And you're dealing with a signal that should quickly connect you with another concept, important concept that I keep mentioning that again and again in medical imaging, signals and systems, and all that. Okay. In medical imaging, we did discuss this in class. Okay. It's a very, very basic concept. Integrator is a low pass filter. Integrator, the errors will get cancelled. The mean error is 0. That is one thing that you need to know, but it's a low pass filter is not necessary. Okay. Here, integrator and that AC op-amps and all that you would need, of course, but here integrator as a low pass filter is not required. But that's a good guess, I should say, because there's uh, active filters using op amps can do low pass filters and all that. But fair guess. But band limited is related to some concept. Can anyone? It's one word, okay, or two words. Can anyone related to that? And let me also say at this stage, these two are related. It has to be 99% accurate. 99% accurate compared to what? Compared to truth. So that is fairly easy. Okay, let's do that. What? 99% accuracy, 2 millivolts. What is the acceptable range? Can someone give that one out? What number is acceptable here? Around 20 millivolts. Very easy part. Right now, in fact, I should put Guru I should give credit to Guru with this one. Guru Karthik, I suppose, right? 99% accuracy of 20 millivolts. So can someone tell me what that target is? Where should the error lie? Or where should the measurement lie? You can give a range for it. Very easy. 20 millivolt plus or minus something. Can you tell me that value? The green tab is still open. Yeah, okay, let's do this. Again, Guru is answering this. That's quite good. So 22 minus 0.01. That is 1 minus 99%. That is 0.01. Okay. That happens to be 0.2 millivolts. So you want a measurement within this range. You want a measurement within T plus or minus 0.2 millivolts. We got that from the expected accuracy. That's how we connected those two numbers. One more concept, actually, let me underline the concept. You're dealing with a signal, right? You're dealing with a signal and you're averaging it. You're dealing with a signal, you're averaging it. There is something called signal averaging. There is noise in the signal, there is noise in the ECG, standard deviation in the noises, so and so. You take n ECG samples, take the average of n samples, the noise decreases because the random things get cancelled on an average. So the standard deviation of noise brings down. If you take n EEG samples and add them together, average them together, take n ECG signals, more ECG signals, if you average them, the noise amount will decrease. Hey, let me write that down. This is something that most of you may not know yet. It's there in the notes. Okay. Signal averaging, noise standard deviation. If you take n samples, if you average n curves, noise will become sigma by root n. This is known as signal averaging. If you quickly Google signal averaging, you on Wikipedia will tell you what signal averaging is. That is, the standard deviation characterizes noise. If you use n sample, the noise kind of comes down. Say n is 1, the original noise. If n is 10, or let's say n is 4, noise halves, right? Like that. Quick question. Does the statement alone make sense? Signal averaging, amount of your noise comes down. Standard deviation of your noise decreases if you average n signals. Does this make sense? How much does it decrease? Sigma becomes sigma by root n. Doesn't make sense? If it doesn't make sense, I can quickly show you that. Let's look at this is compute signal averaging. This is why you take multiple signals because the signals are very noisy. If you take multiple signals, average them, the noise level comes down. Don't need this. Okay, this is complicated. It's hard to if there is any illustration of this. Ensemble averaging. Yeah, there you go. As going elsewhere, but notice quickly. Notice. Let's open this image and let me share that. Just open that image. Let's say you're measuring a EEG signals. Okay, first signal is this. Second signal is this. Third signal is this. Notice it's very, very noisy. You can average them, right? You can add them and find the mean, right? You can average, say, these two signals, find the mean. You can average three signals, find the mean. You can average n signals and find the mean. What happens is, if we average two signals, this is the resulting signal. If we average 8 signals, this is the resulting signal. If you average 32, this is the resulting signal. If you average 128, this is the resulting signal. Random fluctuations get cancelled while averaging. Only the signal remains. Noise gets cancelled. So with more and more numbers in the averaging, samples in the averaging, you get better and better signal. Or there is a reduction in standard deviation. How does that noise reduce? How does the reduction in now, how much does the standard deviation reduce? That's fairly easy to say. It reduces by 1 over square root of n. If we average n signals, your noise comes down by 1 over square root of n. If n is 100, your noise comes down by factor of 10. Square root of 100 is 10, right? So standard deviation of noise comes down by 10. Does this concept make sense? I'm fairly illustrated here, right? Make sense? This is known as signal averaging, theory of signal averaging. This is question on this. Make sense or doesn't make sense? If you use more number of signals, that is, if I average all the signals, I'm going to get, if I average 100 signals, I'm going to get better signal. Noise gets cancelled. How does a batsman perform? It's very hard to say that in one match. If I look at a streak of 10 matches, I can tell how good a batsman he is, right? If I see him perform in 100 matches, I get a much better idea. Fine. So that is another part that you need. And I just kind of explained that theory and I also put it over there. Example, whatever is a noise, that becomes 1 over square root of it. Okay. Let's say the noise standard in typically rate standard deviation of the noise. But let's say noise, okay, becomes noise by square root of it. We'll have to quantify noise. We'll do that in a moment. Noise becomes noise value by square root of it. It reduces by averaging n signals. Great. That is another here. There is one more piece, a band limited signal. Again, see, you're dealing with a signal, band limited signal. This thing should spike. There may not be any instrumentation students, but this is fairly basic, right? At the beginning, image formation, I kind of say this, right? Even if not in, if you are dealing with signals, that is, if you are sampling signals, or dealing with sampling band limited signals, avoid any errors, artifacts, aliasing. You should sample it something. We discussed this in class. Does anyone recognize that? Okay, now I should give credit to Madhu Walala. Should sample it at twice the bandwidth, twice the spectrum bandwidth. If the thing is at 5 kilohertz, your sampling frequency, this goes back to Nyquist, Fs is 10 kilohertz. The rate at which you're getting signal should be 10 kilohertz, at least 10 kilohertz. This also corresponds to, so distance between one sample and other sample. The minimum distance between one sample and other sample is 1 over Fs. Okay. This corresponds to period between gap between samples. That gap is 1 over 10k seconds. Specifically, this number, okay, 1 over Fs. This is the time period of this is the sampling period. Okay. Because 1 by 10k, that is 0.0001. Need a gap of at least this much seconds between two samples. That's the third bit of the puzzle. Now, to complete this, 95% uncertainty. Okay, minimum averaging. This is where the minimum averaging time comes. Okay, going above this is fine. Taking more time to sample, this is no, actually, yeah, this is minimum averaging time comes from two things. Okay, so this is one part of the puzzle. Let's complete this 95% certainty. Okay, that is 2 sigma certainty. I'll also complete that part of the, try to partially complete that part of the puzzle. Let's see if any other student is like, RMS is like sigma for this because it's an integrating voltmeter, because it's a Gaussian noise. Put in very, very simple sense, RMS is standard deviation. So the standard deviation in the noise is 10 millivolt. Okay? If you connect that, okay, your noise, the maximum noise can allow us with, if you have to be 95% certain, the maximum allowable noise is 20 millivolts. This corresponds to 20 millivolts. This is max allowable noise. Max noise. And what the question says is 20 millivolts, you integrate the noise as you average the noise, as you sample the signal, should become 0.02. How many samples do you need so that 20 becomes 0. We write it that one. 20 millivolts comes 0.2 millivolts. The signal average, more number of samples, the thing integrator kind of averages. Okay. That does the averaging part. So how many samples do you need? Can you quickly make that calculation? 20 should become 0.2. Can you make that calculation? Anyone again? This is noise value is maximum acceptable noise value is 20 millivolts. That should somehow become 0.2 by averaging. How many data points do you need? Yeah, your n should be, use the below equation. Again, this is from Guru, that is good. Okay. The Guru is querying twice. Your n should be 10,000. You need at least 10,000 samples with the gap between samples 0.001. The gap can be longer, but that won't give you the minimum time. Okay. So give me 1 second. Yeah, at this stage, actually, you can complete the answer at this stage. The minimum gap between samples has to be minimum gap is 0.001 seconds, and you need 10,000 samples. What is the minimum time required for that? This is the minimum gap between samples. Gap is longer, your frequency becomes smaller. Nyquist is violated, you will have some other issues. So minimum gap between samples. Minimum gap between samples. Okay. It cannot be longer. This is where the minimum time is coming from. If you're wondering where that minimum is coming from, the minimum gap between samples. And you need 10,000 samples. How long will it take? For one sample, it takes 10 power minus 4 seconds. You need 10,000 samples. What is the answer? You are averaging signals in time. You're not averaging signals in space. That is, we're averaging one signal after the other. Okay. This is like, so because it's an integrator, every sample is getting added to one kind of averaging. Okay. So you need to sample a data point here. You need to sample a data point here, and you need to keep on doing that. This minimum distance is 0.001 seconds. Okay. This is sample 1. This is sample 2. And you need 10,000 samples. What is the minimum time required? Notice this is the minimum. This is the minimum time. Okay. Minimum, or in fact, this is the maximum allowable gap. Okay. This is, you can have gaps that are shorter. 1 second. This min frequency, minimum frequency, this is maximum gap. That will give the minimum time taken for the whole thing happens at that maximum gap. Okay. So at least this much gap. Let me simplify this English. This, okay, you need this much amount of gap in the threshold. Other minimum maximum will vary about. Okay. At least this much gap. Actually, max gap. So you need this much gap that technically is maximum gap. Much gap, you need 10,000 samples. That will take 0.0001 into 10,000. That is second. Second unit shows up here. Okay. And that's the answer here. Technically, this is the minimum frequency. You cannot sample it at a smaller frequency. You need to sample it at least this frequency. Okay. You can sample it finer. That is fine. So this corresponds to actually the maximum gap. Okay. You sample it faster, technically you can and get the samples answer faster. So this is okay. This is a minimum average. Can you do this experiment in only this much 1 second? No. You can technically, if you sample it, let's say you do it at 20 kilohertz, you're not going to violate Nyquist. No one stops you from violating Nyquist. That 20 kilohertz, that will make the gap between samples 1 by 8,000, right? That is 5 into 10 power minus 5. That's a smaller number. To get 10,000 samples, you're going to take shorter time. So actually, trying to explain, I noticed this. We can do it here. If you sample faster, technically, you can do it at 0.1. But let's, Right now, this is technically the maximum gap. Is there any like, am I missing something here? I'll also open that to you. This is the maximum allowable gap. Maximum allowable. If the gap is larger, your sampling is slower. Okay, maximum allowable gap. Oh, is this a minimum time? Am I missing something here? Okay, so this is in fact, this is a nice question. Let me also think about zero point 0.1. If we can do this experiment in 0.1 seconds. Okay, looks like I can do, right? I already if you do this at Nyquist only gives you lower limit for sampling. It's not an upper limit for sampling. This is minimum sampling frequency. That's so the maximum gap. Okay, analog signal is so there is one more question. Analog signal is sampled at 100 megahertz to sample 1024 samples. Only the samples are used to evaluate 20 and 24 point FFT. Separation between adjacent frequency points. See, okay, this technically, this is if you sample at 100 megahertz, okay, separation between data points in the Fourier space. Separation again would be 100 megahertz. 100 megahertz. Okay, so there is one question here. Let me answer that. Okay, because I think Madhu kind of said the question that I posed, there is some signal sampling it at 100 megahertz corresponds to a time period of this is say sampling frequency. Okay, a time period is 1 over fs. We're taking a sample every 1 over fs. This is okay. This is 1 over fs. That is somewhat not important for the discussion. But the thing is, take this, do the Fourier transform of this. Okay? Now, Fourier's transform of there are two signals here, the analog signal and then the discrete signal. Say the Fourier transform of the analog signal, let's again, simply put it, let's put it band limited, okay. Fourier transform of the discrete signal, okay, that should look repeated. So notice this axis is in F. This is the discretized signal, that's the continuous analog signal. This you have the analog here and you have the rhythm. So this is kind of repeated. Okay. Now you are sampling this such that there are 4 samples. Sampling this Fourier transform, right? So there are totally 1024 samples. It's your requirement. So each point you have a sample. And what would be the distance between repetitions? That would be 100 megahertz because it's going to repeat at the sampling frequency. Okay, because it repeats at the sampling frequency, you will have a total the separation of 100 megahertz between the bands, and you're sampling it at 1024 samples. And what is the gap between two samples, right? What is this gap? That would be m 100 million by 1024. Okay, so roughly that is 100 into 1000 by 1024. So this is 97.6. This is a question from the Hertz. This is the gap between the samples. Let me also, for consistency, let me give this up. Great. This is somewhat involved. You need to know this analog spectrum, discrete spectrum, discretized spectrum. You have to discretize, just get, DFT, DTFT. There are a couple of confusions here, which I typically avoid to do, but this is what is happening. Okay. So if you sample it at 100 megahertz here, your spectrum is going to repeat at 100 megahertz. So whatever you do, you should do it within that 100 megahertz. If you need 1024 samples there, it has to be at least 97.65 kilohertz. This is this distance. But if you want to do more information on that, would be you need to know what is the transformations that I am showing. Okay, you need to know what these arrows are. That kind of like that would be too much to explain in this class right now. But right now this is maximum allowable gap, right? This is maximum allowable gap. So actually, technically, I feel you should. This is a minimum sampling time, and sample at higher times. Let's say oversampling is there. You don't want to undersample for sure. Oversampling, you oversample, you do it faster, and so your gap will reduce and your minimum time will reduce. So in fact, after describing you, I am puzzled about this. But anyways, we'll kind of come back to that. Okay. So this is good. So this discussion took shorter than I expected. Notice in the real world, you're going to be thrown up with questions like this. Okay, I know there are many features, and you have to connect features.
this feature to that feature, sampling frequency to the amount of error, acceptable error, and you have a battery not working, you have a power cut issue, right? You're dealing with all of this. And then if you are very good at the basics, the fundamentals that you learn in Gate, right? This is still not real world scenario. This is like gives you a sort of a window into a real world scenario, right? But if you're good at all these fundamentals, right? Hey, Nyquist, you cannot do that slower than that. Hey, if you average signals, it's going to get noise is going to reduce further and further, right? So that kind of connection is what is expected out of you, because all the formula, all the concepts that you learn in Gate won't show up in the real world directly. They will indirectly show up as subpoints of subpoints. Okay. So you need to be very good at making all these connections. First of all, to make the connection, you need to be very good at the individual nodes. So be very clear about your concepts. Have a very thorough understanding. And as you start making small connections, your confidence kind of builds up over time. Okay. So build that confidence so that you are kind of equipped. If you are fortunate to find a position in a core job, right? If you manage to find even if you go to a non-core, if you get placed in a non-core industry, any of the things that you learned, okay, will come back and bite you in forms that you don't anticipate. So it's a good idea to know these things very well. Okay, when you have a chance to learn, Gate is just an excuse. When you learn it, make sure that you learn it very well. And I am really happy with the way this session went. I usually have one special session where you kind of see, I want to see how the semester runs, right? This is my way of gauging it, and this is very good. Okay, so in fact, most of our home run hitters are not there. Still, it went very good. Okay, that is good. We need to stop somewhere, right? Scheduled. This is a good place to stop. If there are any other questions, okay, post it in the group. Okay, so have a good one. Take care. Bye. I'll see you again.